Okay, and so in this video we're going to take a look at the idea of conservation of angular momentum. It's a really interesting topic, something that applies to lots of sports like gymnastics, diving, or ice skating, where people want to be able to spin or rotate and then somehow, without touching anything else, be able to control their spin. And so this idea of angular momentum it's a little different than the idea of conservation of momentum, the way we would normally think about conservation of momentum, because normally with that, we're talking about two objects colliding with each other. But in this case, we're not talking about colliding with anybody. I'm not going to, for that reason, I'm not going to take a look at the linear version of angular momentum, because it is a little bit different. We are really only looking at one object, but because the object can expand or either bend or stretch out, that's going to allow us to control the rate at which we rotate. So the idea of conservation of angular momentum is, it should sound exactly like linear momentum, except that the change of the total angular momentum of an object, so in before we would have said of a system, but in this case, we're going to focus on just one object, so the object will always be the system. The total angular momentum of an object will remain constant as long as no outside torques act on the object. So we won't look at objects losing mass or gaining mass. That would be the only way that you would have to deal with the idea of a system. So long as the object stays the same mass and only changes the location of where that mass is at, then we're still looking at only one object. What it's essentially saying is that, remember, angular momentum is I times omega, that no matter what we do, that when we multiply those two things, they will always be equal to a constant. Or that is to say that L1 will always be equal to L2 will always be equal to some constant value. So now we could look at some simple examples, but I feel like the most relevant example is to look at ice skaters. Now the problem with ice skaters is that obviously they're not simple geometric shapes, but we can simplify it down a little bit so you'll at least get the idea of how, how things are working. So when you look at an ice skater, the first thing that they're going to do is they're going to stretch their arms out, and then as they begin the spin, once they start the spin, then what's going to happen is they're going to pull their arms and legs in, and as they pull their arms and legs in, you can see, it's very obvious, it's very noticeable, they get faster. You could do the same thing yourself. If you just took, let's say, two textbooks, and you held one in each arm, and you held them out far from your body, hold them out as far as you can on a chair that can spin. So maybe it could be like a stool or something that is able to spin all the way around, or maybe it could be like a chair that you would have at a desk. But it has to be able to spin around on its own. So if you get your feet up off the ground so that you can spin freely, and have somebody spin you around, and take those textbooks and pull them in close to your body, and you'll see, it's really obvious. You will spin much, much faster as you pull your arms and your legs in, and that's because of conservation of angular momentum. So in order to do this, we're going to simplify the ice skater down. So first of all, the ice skater is going to be represented by a cylinder. This is going to be the body of the ice skater. Just to keep things a little bit on the simpler case, we are going to ignore the legs. But the legs are actually much heavier than your arms, and so they have much more power to cause you to increase your spin. And you will see that ice skaters, when they begin their spin, they have at least one leg or their knee sticking out, and then they start pulling that leg and knee in as they begin the spin. So ultimately, this thing is going to spin around an axis that runs through the center like this. We're going to make this radius 0.25 meters. That's a pretty fair assumption that a person is about a half a meter wide. And so therefore, the radius of this imaginary person who's shaped like a cylinder is going to be 0.25 meters. Now, the length of their arms for a typical figure skater who might have a mass of 60 kilograms would be to have arms, and we're going to make those arms are going to look exactly like long rods. Okay, but they're actually connected all the way to the center. Drew that the wrong way. Okay, so these arms are 0.7 meters long, but realize that they are connected all the way through the center. So we're going to connect the arm all the way through the shoulder to your spine, which is where essentially you're spinning around. And so that that can be changed. So that can be taken to be like this, or it could be taken to be pulled in, and that's going to change things. So ultimately we have two possible situations. So we have arms pulled in, then we just have a mass of 60 kilograms. Arms out, then we have three different things, and each of these three things is going to affect the moment of inertia. So first of all, each of the arms, I looked up to see what percentage of a person's body is their arms, and it says 5%. 5% of 60 kilograms is 3 kilograms, so that's for the right arm. Plus we have the left arm, plus then the remainder of their body is 54 kilograms. Okay, so arms in, arms out, and we're going to calculate first of all the moment of inertia. This is the important thing. We need the moment of inertia for when their arms are in. We need the moment of inertia for when their arms are out. So let's start first of all with arms in. So when your arms are in, it's a pretty simple calculation. It's a simple cylinder. You're going to pull your arms in so they're flat and become part of the cylinder. And so therefore I is equal to 1/2 mr squared. Same thing we've used for every example that we've used so far. And so that's going to be simply equal to 1/2 60 times 0.25 squared to give me 1.875 kilogram meters squared. Okay, arms in, total moment of inertia of 1.875. Now the question is when the arms are out. Okay, well in that case, we're going to end up with two things that we need to add together to get the moment of inertia. The first thing is the cylinder, which is now only 54 kilograms, we still need to calculate. That's 1/2 54 times 0.25 squared. Okay, so that gets their body. Now we need the moment of inertia for these rods. So if you look up in a book, the moment of inertia for a rod being swung around by its end, and realize that this rod is actually 95 centimeters long because it's 70 centimeters from the tips of their fingers to their shoulders, but from their shoulders to the center of the motion. So this distance right here total is 0.95. So we have a rod being swung around like this, with a total length. And so the formula for that is 1/3 ml squared. So you use the length of this squared times the mass, but then it's times 1/3, except that I have two of those. So it's going to be 2 times the quantity, 1/3 times 3 times 0.95 squared. Now, this is like an overly complicated problem. To be perfectly honest with you, if you were asked a problem like this on a test, you will probably just be given the moment of inertia. They'll say that the moment of inertia when their arms are in is 1.9, and the moment of inertia when their arms are out is whatever it is. And they just wanted you to show that you understand the basic idea of conservation of angular momentum. However, if you go ahead and make that calculation, you should find that you end up with 3.312 kilogram meters squared. Kilogram meters squared. We're just doing the moment of inertia. Big difference, right? This is almost double the moment of inertia that you would get by holding your arms out like this. You could actually increase the moment of inertia even more if you hold something heavy in your hands, something like weights or a heavy book or something like that. You'll see that you get even bigger moment of inertia because the more mass you can get, the farther from the center of rotation, the bigger your moment of inertia is. Right? Now also, in the problem, you were told that initially that the skater, when she first started to spin, she was spinning at one revolution per minute. I am going to change that. Let's assume that she is moving at, we're going to say 6 radians per second. The problem with this is that it wouldn't make sense. That's a really slow revolution. 1 revolution per minute is incredibly slow. So I'm just going to change it to 6 radians per second. So what we're saying is 1 revolution per second. That's what we're saying. It was misstated. It should have said 1 revolution per second, which is about 6 radians per second. So if we take that to be the omega, then we can use the idea of conservation of angular momentum, which says that I1 omega 1 is equal to I2 omega 2. Let me move this up a little bit so you can see. So now I have the angular speed, I have both of the moments of inertia, and now I can go ahead and calculate omega 2. Omega 2 would be equal to I1 omega 1 divided by I2. So on this side, we'll have the initial moment of inertia, which was arms out. Remember, the skater always starts with their arms out, and that is going to be 3.312 times the initial, which is going to be 6, divided by 1.875. So we'll go ahead and calculate that really quickly. And that comes out to be 10.6. And that would be radians per second. So as you would have expected, it comes out to be approximately double the angular speed that it was traveling, that the person was traveling at before. What does the ice skater do when she wants to stop the rotation? She throws her arms out. She throws her arms outward or her legs outward, and that will slow her rotation rate down so she can stop herself. Let's say, for example, you're a diver. Okay, so divers jump off the platform or off the diving board, and then they want to start spinning. So they intentionally jump outward so they can put a little bit of torque on themselves to begin the rotation, but that rotation would be pretty slow. But then they tuck their body in. So if you watch a diver, you'll see that they tuck their body in really tightly, and as they do, they begin to rotate much more rapidly. Now, when they get ready to hit the water, they don't want to hit the water all tucked in like that. They want to straighten out and go into the water straight. So at the right moment, then they have to time this. Obviously, it requires a great deal of skill to time this correctly. When it comes time for them to hit the water, they stretch their body out, and as a result of increasing their moment of inertia, by stretching their body out and moving their mass as far as possible from the angle of rotation, then you'll end up with it'll slow the speed down in a way so that they'll be able to be in control when they hit the water. Any gymnasts, divers, ice skaters, they all know how to do this, how to take advantage of either increasing the size of their body or decreasing the size of their body by stretching their arms and legs out in order to be able to control the rate of rotation once they leave the ground or once they jump in the air.